Hey everyone, welcome to my alkene reaction video series. Today we'll be going over hydroboration oxidation reactions, which is the addition of borane to the alkene to form an alkylborane. Then you'll have oxidation occurring to change the carbon to boron bond to carbon to oxygen, which in this case is going to allow you to add an alcohol. Before we start, here are some definitions for you to know. What is an electrophile? It's an atom that is electron poor. It is an electron pair acceptor and it carries a partially positive charge, or a positive charge as well. Nucleophile, an atom that is electron rich. It is an electron pair donor and it carries a lone pair or a pi bond, and it doesn't always carry a negative charge. Like for example, in this reaction, alkenes will be our nucleophiles. Make sure that you know what Markovnikov's rule is as well, which just states that for unsymmetrical alkenes, the electrophile will attach to the less substituted carbon atom, and the nucleophile will form a bond to the more substituted carbon atom for stability. And an anti-Markovnikov reaction is the opposite of that. What is a carbocation? It's an ion with a positively charged carbon atom. Okay, so before we start anything, let's get down the general idea of the reaction. So in the hydroboration reaction, two bonds are broken. It'll be the hydrogen to boron bond in BH3 and the alkene pi bond. After that, two bonds are made, the carbon to hydrogen bond and the carbon to BH2 bond. But it doesn't stop there. BH2 can keep reacting with alkenes to form a trialkylborane. So this is the end result of hydroboration. Afterwards, oxidation will occur with a polar protic solvent, most commonly used H2O2 and H2O, and an OH ion occurs and turns the carbon to boron bond into a carbon to OH bond. And for thermodynamic purposes, this reaction is exothermic, meaning that the bonds broken release less energy than the bonds formed. So I'll go over the general reaction for you guys. Take note that the hydrogen atom has a partially negative charge on it, and the boron atom in BH2 has a partially positive charge. That is not a mistake. I will go more into depth as to why this is later on once we start going into hydroboration itself. So just for now, the hydrogen atom is going to attack the pi bond. The pi bond in the alkene will break. And now this carbon atom is going to want to form a bond with BH2. You end up having this transition state where obviously there's no carbocation arrangements occurring. And now you're going to have BH2 and hydrogen bonded to the adjacent carbon atoms. And so this is not where BH2 stops. It has two more hydrogen atoms, so it's going to want to form more bonds with the same alkenes. So as you can see here, another alkene is attached to boron, and it has one more hydrogen atom, so then it gives it one more go, and bam, you have a trialkylborane. So then after that, now is the oxidation aspect of the reaction. So you're going to use H2O2, then you're going to have an OH ion. It can come from NaOH or KOH. Those are the most common ones. And you'll end up with this product. Okay, so let's talk about the hydroboration aspect of this reaction. So just as a reminder, no carbocation arrangements are formed. There is only the transition state that is formed. That transition state will be right over here, in which case you have a bond forming with hydrogen and BH2, where the pi bond used to be. So these carbon atoms are going to want to form a bond with these atoms. And of course, you'll have a partially positive carbon atom and a partially negative one. And because I've been stating that hydrogen has a partially negative charge, this carbon atom is going to want to form a bond with that hydrogen. This carbon atom is going to want to form a bond with this atom. So, why does this transition state form? So, take note that boron only has 6 valence electrons. It's happy with its 6 valence electrons. So then, you will have an sp2 hybridized boron atom. So, if you take note, there's 2 empty orbitals here. And so the pi bond in the alkene is going to attack these unhybridized orbitals. And it's going to make boron lose a hydrogen atom in the process. The hydrogen atom then attaches to the more substituted carbon atom, while your BH2 group is going to attach to a less substituted carbon atom, which is exactly what is occurring in this transition state. Okay, so now let's talk about the reason as to why I have a partially negative charge on hydrogen and a partially positive one on boron. Kind of weird, right? Well, the reason why it occurs is because hydrogen is more electronegative than boron in BH3. You're comparing a 2.2 electronegative charge on hydrogen to a 2.0 on boron. Therefore, that is why hydrogen has a partially negative charge and boron has the partially positive. And for this reason, this is why this kind of stimulates a anti-Markovnikov addition, because of the reason that you have hydrogen bonding to the more substituted carbocation. And of course, this anti-Markovnikov addition is going to occur in unsymmetrical alkenes. So as you can see here, after hydrogen and BH2 are bonded to the adjacent carbons, the 2 hydrogen atoms in BH2 are going to want to keep reacting and form this trialkyl borane right over here. Now, most professors won't ask you to go too much into depth with this reaction. They'll just want you to know what kind of reactants you have in the beginning and then what products are formed at the end. But for those who want to get more of a fundamental understanding about this reaction, this video will serve you right. Okay, so let's talk about the oxidation reaction. So you start off with peroxide, and then you have either NaOH, KOH, lithium OH, any of those kind of ions. And so just take note that Na and K in these ions are going to be spectator ions. So, meaning that they are going to disappear in this reaction. And then what you will be left with, and what's important here, is that you have a OH ion. So this OH ion is going to attack one of the hydrogens in peroxide, making the bond break, expelling the electrons back to oxygen, therefore giving you this peroxide ion. Cool. So now you have that. And now you also have a water atom. Cool. So let's look back at this trialkyl borane. It's still sp2 hybridized. It has 2 empty orbitals, right? So this peroxide ion is going to want to attack one of those orbitals. And so boron is unhappy with 4 bonds. What's going to happen now is kind of crazy. So the carbon atom in one of the alkenes, we're going to talk about this one, is going to want to form a bond with this oxygen atom. This oxygen atom is going to expel the electrons from this bond back to the OH ion, in result, giving you this kind of bond. So now, instead of having carbon in this alkene bonded directly to boron, now it's bonded through oxygen. But now boron is happy because it only has 3 bonds. So this is the reason why this occurs. And in result, just notice that you have an OH ion as a byproduct. Okay, so this occurs 2 more times. And so what happens next is that OH ion is going to once again attack one of the unhybridized orbitals, and it's going to expel one of these. So as a result, you have a BOH now. This is going to happen, as you can guess, 2 more times. And you're going to be left with this as a product. Okay, so that's not the only product that you get. Obviously, just notice that in order to make more of the ions here, don't forget that you had water in the beginning as one of the products from reacting your peroxide with the OH ion. And also as a result of kicking out your oxygen atom here, you're going to have this react with water, and it will give you this as a product too. Okay, so let's just rewind a bit. I know that this was a lot to take in, so I just want to take time to go over it once again. So you have a peroxide ion, and you have a water atom form from reacting peroxide and this OH ion. The peroxide ion is going to attack one of the unhybridized orbitals in boron. And because boron doesn't want to have 4 bonds, you're going to have one of the carbon atoms in the alkenes want to form a bond with that oxygen. Giving you this as a product. It's going to do it 2 more times. And so you're going to have all these oxidized alkenes bonded to boron. And so the OH ion is going to once again attack the unhybridized orbital in boron, and it's going to expel this whole group. So after that, you have BOH bonded to each other, and it's going to keep happening again, where now in order to get another OH ion, you have this happening on the side where you have this alkoxide ion, which was expelled from the boron atom earlier. You're going to have this alkoxide ion want to take one of the hydrogens from water. You'll have a formation of an OH ion. And now this OH ion is going to keep this reaction going, ending up in this, and then eventually this as your final product, where you have all OHs bonded to boron. And so because of this reaction here, your products are going to be this OH ion, it's going to be this OH alkene, and it's going to be this as your final product. Okay, so let's talk about the stereochemistry aspect of this reaction. So for the hydroboration aspect, there will be a syn addition. So let's look at this methyl cyclohexene for a second. It's going to react with BH3 and THF, tetrahydrofuran. And in the transition state, you'll have hydrogen wanting to bond with the more substituted carbon atom. and the BH2 bonding to the less substituted carbon atom. So, as a result, you'll have a syn addition because they're going to attach onto the same side of the molecule. In this case, they were both bonded on the front side. They did a front side attack. Just take note that you could also have a backside attack on both of them. So this would be the other result of the backside attack. And just as a reminder, these two are enantiomers. So for the oxidation aspect of the reaction, you have your H2O2, your OH ion. And so the OH ion is going to add upon the same side that the previous hydrogen atom added onto. So it also does a front side attack in this molecule. Here you have it, syn addition. And if you look at the backside attack, same side. Okay, so as a result, this is the general reaction. This is most likely what most students will see or be given by their professors, where they have a molecule, they give you the reactants here, BH3, tetrahydrofuran, H2O2, NaOH, and they'll ask you, what is the product? So if you see these shall be your answers. Okay, so now that we went through all of that, I want you guys to try out a problem for me. So draw a stepwise mechanism for this reaction. If you don't want to draw the stepwise mechanism, just draw me the product. What would the product be for this reaction? All right, pause the video and give yourself a moment to solve this. Okay, so let's start talking about the answer to this. Take note that here you have a CH2 molecule. So which one is your more substituted carbon atom and which one's your less substituted carbon atom? This one would be your more substituted carbon atom. And since I haven't been talking about the degree that they are, this will be your third degree. This will be your first degree. Okay, so now you have HBH2, going to want to form a bond with these carbon atoms. The pi bond right here will break, and so you'll end up with this transition state here. Of course, as always, your hydrogen atom is going to bond to the more substituted carbon atom in this reaction, and your BH2 is going to form a bond with the less substituted carbon atom. So they're going to add in a syn addition. You're going to have hydrogen and BH2, in my case, do a front side attack. They could also do a backside attack. I just chose to do a front side one. And now, of course, because you have 2 more hydrogen atoms on BH2, this reaction will keep going to form a trialkylborane. And so, bam, you have this crazy thing here. Okay, so remember, you're going to have a peroxide ion formed, and it's going to attack one of the unhybridized orbitals on boron. And now one of the carbon atoms on the alkanes here are going to form a bond with this oxygen atom, expelling this OH. Giving you this. And so now that same reaction is going to happen 2 more times. And so, because you had an OH ion as a product at the end, the OH ion is going to attack one of the unhybridized orbitals on boron. And it's going to expel one of these groups here. It's going to form a BOH. This is going to happen 2 more times. Give you 3 BOHs attached to your boron. And your final products. Right there. Alright guys, if this video was helpful to you, please give a thumbs up, subscribe. If you have any questions, please leave your questions in the comments below. I will try to get to you guys as soon as I can. If you have any suggestions for me on making future videos, please let me know. Thank you guys, and have a nice day.